Hello and welcome to my YouTube channel. After a very long time I am going to continue with the playlist for simulating Arduino using Proteus. In this video we are going to see how to simulate fading LED using Proteus. So let's start the video. To generate fading effect, we need to have this analog write function in the microcontroller. So, how can a microcontroller generate an analog output? Because we all know that microcontrollers are digital devices. Then, how can they generate analog output? For that, we have to understand that microcontrollers or microprocessors both are digital devices. Hence, they cannot generate pure analog signal. This is the first thing to understand, that microcontroller and microprocessors cannot generate a pure analog signal. Instead, they can generate a signal which is also known as pulse width modulated signals, which can be translated to equivalent discrete analog signal. Remember, these are discrete analog signal, they are not pure analog signals. So, in short, we can say microcontrollers and microprocessors, they generate pulse width modulated signals. So, we have to understand the concept of pulse width modulation. So, pulse width modulation or PWM signals, in short, are generated by varying the duty cycle of square waves. Okay. So I hope you know the concept of duty cycle. Otherwise, you can go to my channel and I have discussed about duty cycles in one of my lectures. Okay, so by changing the duty cycle of the square waves, we can change the overall average signal or average DC value of the signal, and that can be considered to be an analog signal. So might be possible with this definition you are getting more confused. So let us go a bit deeper. So first of all, we are going to talk about the DAC pins or PWM pins in case of Arduino Uno. Okay, so how to identify those pins which can generate PWM signals. So remember, you have to check this sign, tilde sign, in the Arduino board, and those pins which have these signs can generate PWM signals. So remember pin number 3, 5, 6, 9, 10 and 11. Here you can see these pins have the tilde sign along with them. So 3, 5, 6, 9, 10, 11. Only those pins can generate PWM signals. Rest of the pins can generate digital signals, but they cannot generate PWM signals. Remember, only these 6 pins can generate your PWM signals. Okay, so let us try to understand the concept of PWM signal. So what is the basic concept of PWM signal? Let me go through a very basic example. So suppose the DC signal is always staying on 0 volt, then in that case the average DC value of this signal is also 0 volt. Now, if we increase the voltage to 5 volt and keep it on 5 volt, then in that case the average voltage in this case is 5 volt. But what will happen if I generate a pure square wave, which will have 0 volt and 5 volt both have 50% duty cycle? That means 50% time we have 5 volt and 50% of the time we have 0 volt. In such case, when we have a pure square wave, in that case the average DC value is 2.5 volt. Okay, which is represented here by the pink line. So now, though we have the square wave the average value of the signal or average DC value of the signal is 2.5 volt. So the same concept can be used to generate PWM signal. Suppose we have 5 volt, which is assume that we have less time period for 5 volt and a longer time period for 0 volt. In this case, this pulse wave will have a lower average DC value. Okay, now suppose we generate another signal. After some time we generate another signal in which we have small time period for low voltage and longer time period for 5 volt, which means it has got bigger or larger duty cycle. In that case, the average DC signal of this square wave, okay, will be higher than 2.5 volt. So in time domain, we can see for the time period when the pulses were having shorter time period for T on, which is 5 volt, we had a very low average DC voltage, whereas when we increase the duty cycle, suddenly the average DC value also increased. So assume if we apply the same concept and keep on changing the width of the signal, okay, then in that case we can have a sine wave kind of signal, which will be the average DC signal of the square wave itself. So this is called pulse width modulated signals, because here you see the width of the pulse is changing. Here we have lower width, okay, or smaller width, and here we have larger width, okay. So here the average DC value has increased. So maximum average DC value is here, whereas the lower the pulse or the smaller the duty cycle, we have lesser the DC value. In this way, the pulse width modulated signals can generate discrete analog signals. Okay. Now, apart from that, we have to understand one more basic fundamental, that is called the basic mathematics for DACs. Whenever I say DAC, these are the pins which are used to generate or convert digital signals to analog signals, because microcontrollers or microprocessors are digital devices. So they can generate stream of digital or zeros and ones, and using the pulse width modulated concept, we can generate analog signals. So those pins are also known as DAC or digital to analog pins. Okay. Now, Arduino Uno, in this case, we are talking about Arduino Uno. It has got an 8-bit DAC. So what is the meaning of 8-bit DAC? So remember here, 8 is nothing but a number. We can call it n bit. So different microcontrollers can have different number of bits in the DAC. Here we are talking about Arduino Uno, so it has got 8-bit DAC, which can generate 2 to the power 8, that is 256 different levels. Or we can say it can generate different levels between 0 to 255. Okay. So remember one more concept, that Arduino Uno uses plus 5 volt as the reference voltage, or we can call it Vref. Okay. So Arduino Uno uses plus 5 volt as the reference voltage. It has got 8-bit DAC, which can generate 256 different levels. So using these two values, Vref and number of levels, we can calculate the voltage for different values of DACs which are sent to the DAC pin. So suppose whatever be the value that you want to send to the DAC pin, to convert it into the analog voltage, just multiply that value which is sent to the DAC pin by Vref, which is 5 volt here. So Vref by 255, that is 2 to the power the number of bits, because here we have 2 to the power 8 minus 1. Okay. So by this equation, we can calculate the equivalent analog voltage for any number which is sent to the DAC pin. Okay, so for example, this equation can be reduced in this way, where Vref here, Vref divided by 2 to the power the number of bits in the DAC minus 1, which is 255 in our case, is known as the resolution of the DAC. Okay, so the resolution of the DAC is nothing but voltage reference divided by 2 to the power number of bits in the DAC minus 1. Vref in our case is plus 5 volt, but it may vary. Okay, so depending on the Vref of any DAC, we can replace 5 volt with that value, and even the number of bits can change, so we can replace the value of number of bits in this equation. So remember, Arduino Uno can generate 255 different voltages between 0 to 5 volt, which is our Vref. Okay, so 0 to 255 values between 0 to 5 volt. So please go through this slide once more so that you can clarify the doubts. Now, what are the different applications of PWM signals or analog write? It is used to drive buzzers or loudspeakers or speakers with different loudness. We can control the speed of the motors. We can make them faster. We can make them slower. We can change the intensity of the LEDs. We can make them brighter or lower brighter. Okay. Similarly, we can control the direction of servo motor. We can generate analog waveforms like sine wave, triangle wave, any other different waveforms. Okay, we can generate audio signals with different tones, or we can call it different frequency values. And of course, it can be also used in telecommunication or whenever you are transmitting some signals by using encoded messages. Okay, what are the advantages of PWM? PWM, of course, help us to control the intensity of LED. It also provides high input power factor. Okay, I am not going into that part here. Okay, PWM signal also helps the motor to generate maximum torque. Okay, maximum torque even when they are running at lower speed. So it is not only the speed control, we can even maximize the torque of the motors using PWM technique. What are the disadvantages? Of course, PWM signals are generated with high frequencies, so switching losses are too high in that case. Okay, and of course it also induces radio frequency interferences. Because we are working at a very high frequency, it may generate EMI or EMC related issues in the nearby devices. Now let us try to understand or try to explore how to simulate the fading technique or PWM related signals using Proteus. So for that, you can open the Proteus, and in the first lecture of this particular playlist, I have shown you how to generate this particular project. Okay, so this is the basic project, and in this we are going to load the source code for PWM signal. For that, you can use the Arduino. Go to Arduino IDE, examples, basic, and then you can go to fade. Open that file. Here is the file. Copy that, Control A, Control C, and then paste it on the source code in the Proteus. That's all. Then after that, here you can see I have just changed few values. For example, pin number 9 is used to connect the LED. Okay, why? Because pin number 9 can provide you PWM signal. Apart from that, you can use 3, 5 and other pins which are having that tilde sign. Then let us build the program. For that, you can come to top here and click that button, and in the bottom you can see the status of the compilation. And once the compilation is over, we can simulate or run this program and see the effect of PWM on the LED which is connected to pin number 9. So here we can see the message shows the compilation is completed and compiled successfully without any error. So we can come to this particular schematic and run the program. And you can see the brightness of LED is changing due to fading effect. Apart from that, if you want to connect a speaker and want to see or hear, the effect of PWM on speakers, then you can go to speakers and take this speaker, which is speaker active loudspeaker model. Okay. Place it here, then double click, and then we can change the wire label to 0 volt, or you can just name it ground, GND. And here we can see we have the ground pin. Okay, so right click and we can place wire label here also, GND. So now indirectly this pin and this pin in the loudspeaker are connected together. Now we need to connect this pin of the loudspeaker to the pin number 9, which is here IO9. Okay, so I will give the name IO9 here and OK. And then after that we can simulate the system. So let me just zoom in and then simulate. Okay, so please try to simulate this program, and then apart from that you can play around with the delay. So delay will change the speed by which this particular fading effect will change. Along with that you can even change the fade amount so that you can make the process faster or slower. And you can even observe the waveform on IO9 using the CRO or DSO. For example, here you can just go to probe virtual instrument and you can use oscilloscopes and then connect it to pin number 9. So place IO label IO9. In this way, you can explore more features of this particular functionalities. Okay, just let me stop the speaker because it is making noise. So I will delete this wire and you can see the effect of PWM pulse width modulation taking place on pin number 9. So please explore this particular simulation more, and if you have any further doubts or if you want any further clarification, then you can post your comments or suggestions or queries in the link provided. So if you have not subscribed the channel, then I would like to request you to please subscribe the channel and please share your comments and opinions in the post. Till the next video, stay safe and have a nice day. Thank you.